If you need to hear some good news today, well, here it is. We have arrived at the last section for college algebra. That's pretty exciting. In section 5.4, we're going to learn how to solve exponential and logarithmic equations. Starting in section 5.4.1 with solving exponential equations, we're going to consider two cases. The first case that we're studying here is when we can achieve like bases. We'll look at another method if we cannot achieve like bases in later videos. Here's how we're going to approach an exponential equation. Rule: if a to the mth power equals a to the nth power, then m equals n. So if the bases of an exponential equation are the same, then logically it follows that the exponents are also equal. So our goal is to achieve like bases on both sides and then set the exponents equal. On example 1, we're going to solve the following exponential equations exactly. Notice in example 1a, the bases are the same. 5 to the x plus 3 equals 5 to the 7th. So we're going to observe that it must be true that x plus 3 equals 7. Make sure you understand there that I did not divide both sides by 5. I haven't canceled the 5 in any way. This is just a logical observation. If we divide both sides by 5, the 5 doesn't actually go away. For example, 5 to the 7th divided by 5 is 5 to the 6th. So again, we're making a logical observation that the exponents are the same. We can solve this by subtracting 3 from both sides, and then we end up with the solution to the equation. Notice if we plug 4 back into the original equation, we have 5 to the 4 plus 3, which is 5 to the 7th, and that clearly equals 5 to the 7th. So that's a pretty easy, straightforward equation. On example B, we have 2/5 to the 3x plus 1 equals 2/5 to the negative 4. Again, we have like bases. Therefore, it must be true that the exponents are the same. This leads us to a linear equation. We can solve this by subtracting 1 from both sides and then dividing both sides by 3. Notice if we plug negative 5/3 back in for x, 3 times negative 5/3 is negative 5, and negative 5 plus 1 gives us negative 4, which is the same thing that we have over on the right side. So negative 5/3 is the solution to the equation. Both of those examples were simple and straightforward because we began with like bases. On examples C and D, we're going to have to do a little bit more prep work before we set the exponents equal. Notice these are exponential equations because the variable is in the exponent position. So our goal is to write both sides as a power of a common base. Now make sure you think about powers and not multiples. On the left side, we have 3 to the x plus 1. That's base 3. So we want to try to write 27 as a power of 3, not a multiple of 3. You might be thinking 3 times 9, but we want to think power of 3. 27 is 3 to the 3rd power. So I'm going to rewrite 27 as 3 to the 3rd power, and then recognize we still have that outside power, x minus 3. Over there on the right side, notice we have the case where we're raising one power to another power. In that case, we need to multiply the powers. And to do that, we need to execute our distributive property. So we can simplify this as 3 to the 3x minus 9. Now, we have achieved like bases. Now we can set the exponents equal. Notice I am switching colors here just to draw your attention to this step. I'm going to say logically, then the exponents must be the same. To make sure that you understand, we did not divide both sides by 3. We haven't done any sort of operation. We're making an observation. If the bases are the same, then the exponents must also be the same. This leads us to a very simple linear equation. We can solve. I'm going to collect my x's over here on the right side so that I'll have a positive coefficient. I'm going to add 9 to both sides. So we end up with the equation 10 equals 2x. Dividing both sides by 2, we get solution x equals 5. Now remember, you can certainly check this with your calculator. So I'm going to take x equals 5 and plug it back into the original equation everywhere I see the x. So the left side evaluates to 729, And then on the right side, again, plugging 5 in for x and seeing the output, we get 729. So both sides are balanced. Now remember, 729 is not the solution. The solution that generated that balance was x equals 5. So in that one, we had to do some prep work to achieve like bases and then set the exponents equal. Looking at example D, we'll do the same thing. 32 to the 2x equals 16 to the x plus 3. When you look at 32 and 16, your mind probably thinks they're both multiples of 8, or maybe you think of multiples of 4, or multiples of 2. Those would all be correct, but again, we're not thinking multiples. We want to think in terms of powers. So I want to express both sides as a power of a common base. Notice that 2 to the 5th power is equal to 32. So I can rewrite 32 as 2 to the 5th power. And then 16 is 2 to the 4th power. Now, if you're not familiar with powers, I do encourage you to sit down and practice the powers of 2, the powers of 3, the powers of 4, so that you'll be familiar with those numbers. Now, again, we have a power raised to another power, so we need to multiply those powers. On the left side, we have 2 to the 10x, and on the right side, with our distributive property, we have 4x plus 12. We have achieved like bases, therefore, we can say then, logically, the exponents must be the same. 10x equals 4x plus 12. We can solve this little linear equation by subtracting 4x from both sides and then dividing both sides by 6, and we come up with the solution x equals 2. Then we can easily verify that solution with our calculator. So I'm going to the original equation and I'm plugging in a 2 for x. Now we get a big number output on the left side, but we're not really interested in the output. We're just interested in the fact that the outputs are the same for both sides. So plugging 2 in for x on both sides yields the same output, or a balanced equation. Therefore, we know our solution is correct. Okay, let's try this with some fractions. On example E, we have 5 halves to the x equals 4 over 25. Now, we're looking to write both sides as a power of a common base. And notice 5 and 25 have a common base of 5, and 2 and 4 have a common base of 2, but they're in the opposite place in the fraction. So what we're going to do is rewrite the right side. First of all, just to be clear, I'm going to write it as 2/5 squared, right? 2 squared is 4 and 5 squared is 25. But 5 halves and 2/5 are not like bases. We know that we can invert a fraction when we negate the exponent. So I'm going to flip the base over and change the sign of the exponent. Then we have achieved like bases. And look how easy our solution becomes. Again, we can logically say the exponents must be the same. So we have solved the equation for x. Now, a quick check on our calculator. The left side I'm going to type in as 5 halves raised to the negative 2. And that gives me 0.16. And notice on the right side, 4/25 has the same value. So don't forget about using a negative exponent to invert a fraction. This will be helpful on the next example as well. I see base 25 on the left, and I see a 1/5 on the right. Well, we know there's a common base between 25 and 5. Of course, that's 5. So I'm going to rewrite the 25 here, as 5 squared, and then I'm going to keep the same outside exponent. So the 25 becomes 5 squared, the outside exponent stays the same. Now, 1/5 could be rewritten as 5 to the negative 1 power. Multiplying powers carefully with our distributive property on the left, we have 5 to the 2x minus 2 equals 5 to the negative 1. Once we have achieved like bases, then we can say, logically speaking, the exponents must be the same. So solving this equation for x, notice this is a linear equation in one variable, so my goal is to isolate x. I'm going to add 2 to both sides and then divide both sides by 2. Our apparent solution here is 1/5. let's double check and make sure that that is the correct answer with our calculator. So going all the way back to the original equation, I'm going to type in 25 raised to the 1/2 power minus 1 and observe the output. And I'll enter the 1/5 from the right side and observe that the output is the same. Thus, we have a balanced equation and we can be confident that our solution is correct. Okay, if you want to take this opportunity to pause the video and work the next 2 exponential equations and test your skills, and then turn the video back on and see how you did. So looking at 7 to the x equals 343, and our goal here is to get like bases. Since 7 is prime, the only like base that would be a potential like base here is 7. Now, you may not be familiar with the powers of 7. Maybe the first one, 7 squared is 49, but you can certainly use your calculator just to experiment with powers of 7 until you find the right one. Notice 7 to the 3rd power equals 343. So we're going to leave the left side as is. That's already base 7. And we're going to write the right side as 7 to the 3rd power. Once we achieve like bases, we can make the observation the exponents are clearly the same. So that one wasn't too bad, other than having to deal with maybe an unfamiliar power. Now, how did you do on the next example? This one's pretty tricky. What in the world would be a like base between 4 and 1? Well, if I have base 4 on the left side, can I write 1 as a power of 4? 4 to what power gives me 1? Did anyone figure it out? 4 to the 0th power. Anything raised to the 0th power, remember, is equal to 1. I don't know. Maybe you figured that one out. I think that one's tricky. Let's finish it off. Now we're going to say, logically speaking, the exponents then must be equal. Now that we have transformed the problem of having an exponential equation into the problem of having a linear equation, we can then isolate x. Add 2 to both sides, divide both sides by 1, and we get x equals 1. Notice up here, if I plug in 1 for x, 2 times 1 minus 2 is 0, and 4 to the 0th power is equal to 1. So we have easily balanced that equation. Now, all of these equations that we've looked at here have one thing in common, and that is we were able to achieve like bases. Well, what happens if you cannot write both sides as a power of a common base? That's what we'll learn how to do in the next video.